Hello everyone, welcome to the video abstract of our paper. My name is Yunxiang Liu and usually I go by Leo. The title of my paper is Improved Automatic Detection of GPS Satellite Oscillator Anomaly using a Machine Learning Algorithm. The first question you might have is that why machine learning? Since oscillator anomalies cause phase disturbance, a threshold could be used to find the disturbed measurements. The problem of this approach is that first, most of the satellite oscillator anomalies we observed have very small magnitude of phase deviation. And second, disturbance could be caused by satellite oscillator anomaly or scintillation. Thus, conventional threshold-based method has low detection rate on small anomalies and requires multiple nearby receivers in order to distinguish satellite oscillator anomaly from phase scintillation. As a result, we tackle this problem by using machine learning, where a single GNSS receiver is employed to detect the satellite oscillator anomaly with a high detection rate. Here is the design satellite oscillator anomaly procedure. It involves two stages. Given the phase measurements as input, the first stage is to distinguish the oscillator anomaly from no disturbance and scintillation. Here, features of power spectral density and ratios are extracted and input to the random forest to conduct the classification. Once oscillator anomaly is detected, we move on to stage 2 to differentiate satellite oscillator anomaly from receiver oscillator anomaly. This is based on the fact that a receiver oscillator anomaly should simultaneously show up on measurements from all satellites in view, while a satellite oscillator anomaly is only present on the measurements from that particular satellite. So we can check if the same anomaly is observed from multiple satellites to identify whether it is the satellite oscillator anomaly. And we call this detection method random forest. As you may notice from the title, it started with the word improved. So it is improved over a previous method named SVM, RBF, SVM. As highlighted in the red box, SVM, RBF, SVM requires two stages to detect the oscillator anomaly, while the improved method, random forest, simplifies it to a single stage. In addition, better detection performance is obtained by the improved method, random forest, as illustrated in this slide. Accuracy, false alarm rate, F1 score are illustrated for both dual and triple frequency signals. Here, F1 score is defined as the harmonic mean of recall and precision, and is usually used to evaluate the performance of an imbalanced dataset, which is the case of this dataset. The last column is random forest, and second last column is SVM, RBF, SVM. Clearly, random forest shows better performance. The other 5 columns are machine learning algorithms used to compare against random forest, where the same features are used as input. Again, random forest is the best. Given the accurate detection method, we apply this random forest to our database to conduct automatic satellite oscillator anomaly detection. Here is a word map showing the stations we processed. Number of days and the year of data are also listed. We process data from these 9 stations. In total, more than 2,500 days of data are processed. The random forest with dual frequency is applied to measurements collected by each station independently. This slide shows one example of satellite oscillator anomaly from PRN6 observed by 4 stations on July 2nd, 2017. At this time, satellite PRN6 is located to the south of Mexico. Although different noises are present, the measurements from 4 stations share the same shape of anomaly at the same time, around 1921 UTC. This observation shows that this is indeed a satellite oscillator anomaly. For this anomaly, the maximum phase deviation is around 0.1 cycle, and the event duration is around 7 seconds. Here is one of the detection results. A satellite-wise average number of satellite oscillator anomalies per visible day is shown in this plot. A few observations from this plot. First, no verified anomalies are found from Block 2RM satellites. Second, no verified anomalies are found from PRN8 and 24. This might be because PRN8 and 24 use cesium clocks, while the rest satellites in Block 2F use rubidium clocks. Third, on average, 1 to 12 satellite oscillator anomalies are observed per visible day. And finally, the station in Tolulu, Chile, observes most frequent oscillator anomalies from nearly all satellites. This is because a nearby station at La Serena, Chile, which is only 20 miles away, provides long overlapping on coverage. This is the end of the video abstract. If you are interested in our work, more details can be found from these papers. If you have any question, feel free to reach me at this email, and you can also explore more interesting research works from our Sense Lab website. That's all I have. Thank you very much for listening.